Good afternoon, everybody. My name's Kay, as just been said. I'm going to be talking about hacking game console peripherals today, specifically PlayStation 4 controllers and their sort of authentication scheme that was introduced quite a while ago. So let's just get straight into it. So who am I, for the people that don't really know me? My name's Kay Ward. You can find me at Kzone pretty much anywhere online. Pronouns are they and she. A little bit of an update from last time I did a talk, but a little bit about me. I'm a BSc computer science student here at UC, which is a little bit strange, standing on the stage. I'm mostly used to business lectures happening around here. So I'm an embedded dev primarily, so firmware development, that kind of thing, embedded C, it's mainly what I do. But occasionally I do a little bit of game dev as well. I did an internship at Cerebral Fix here in town last year. That was a good time, and it's where I also picked up fighting games, which has been an interesting effect on my life. Wouldn't recommend it. And that'll factor into this talk a little bit. We'll see how that happens. So why do we care about hacking peripherals? I mean, it's just a controller for playing a video game. Well, the main reason is peripheral licensing. So this was introduced on the PlayStation 4, which came out in 2013. And it's designed as an anti-counterfeiting measure. So back on the PlayStation 3 and PlayStation 2, you had every brand under the sun making their own weird little copycat that sort of looked like the original controller, but was not anywhere close to it. If a controller fails this sort of licensing check and authentication step, it'll start an 8-minute timer on the PS4. And if you continually just fail every single authentication check throughout there, it'll just disconnect your controller. So after 8 minutes, you're done. It just locks you out. It's definitely not to make money. It's definitely not to make a little bit of extra money on the top of controller sales. It's entirely anti-counterfeiting. Don't ask Sony about that. So why do I care? Why do I care about this? I mean, Sony wants to make a little bit of money, or they want to prevent other people from making money off their own brand. Well, the main reason is custom controllers. So DIY or open source controllers. This is a really popular thing in the fighting game community, particularly. A lot of people will design and build their own controllers and bring those to tournaments, and it's usually either for ergonomics. For example, I can't use a standard gamepad for those types of games because it causes my hands to really clamp up and really hurt. Could be for cost. I mean, standard arcade sticks off the shelf, $150, something like that. And could just be for fun, sometimes you're on a project. Fighting game tournaments near universally use the PS4, and it's shifting over to the PS5 now, but that's the platform it's been on for a long time, so every controller has to be designed for that platform, and it has to work on there if you want to play competitively. And because you have to have a license to make an actual device for the PS4, that kind of locks people out from playing in tournaments if they can't get around this authentication system. I do just want to show off real quick, indulge me real quick here, a few interesting controllers that have shown up at tournaments over the years. For example, this one. This is an Xbox 360. A few of these showed up at EVO this year, which is sort of the biggest fighting game tournament around. A lot of people playing on drilled out Xbox 360s with buttons in them, apparently very popular. There's this thing, which is 50 buttons. It's entirely designed for playing one character in one game, and it's also built into a pizza box. This went viral because of a video the person who made this posted. Very interesting. And this is something I did. This is an HP DeskJet printer. One of my old flatmates in halls just down the road happened to have this lying around, and apparently it didn't work anymore. So I figured I needed a controller. I made this thing, took it to a tournament, and won a match with it. Took this to the... Thank you, I think. So let's actually get into the meat of this talk. What are the workarounds for this kind of authentication scheme on the PS4 in particular? But I mean, other consoles are starting to do this. The Xbox is doing this as well, I think as of last month. The sort of simplest one that people would first think of is pad hacking, which is where you take an original gamepad, like a DualShock 4 or something similar, and you hack it. And it is exactly what you think it is. It is soldering wires to the PCB of a controller and just sticking your own buttons on there. So you can make any kind of custom controller you want, but it's not great. It works, but it's a little bit janky. This was also something I did. This was a $25 controller I found in the bargain bin at EB Games, and I played multiple tournaments with this as my board and my controller. Wasn't the most reliable thing in the world. The proper thing to do is buying an off-the-shelf board, so something that is designed for this kind of custom controller building. You can just buy a board off the shelf and it'll have nice little pin headers and everything. This one's the Brook USB Fusion, which is the sort of gold standard generally in the community at the moment. So it has all your inputs, you just stick them on the pin headers, there you go, and it handles all the authentication for you. And we'll sort of get into how vendors like this do that a bit later, because they don't have a license. Sony will not give a license to people who sell boards like this. You have to be selling an entirely complete controller, and you must stick their fancy little logo on the box and pay them a very large sum of money, presumably, for that privilege. What are the pros and cons of these two approaches? Well, pad hacking is very cheap. It's 25 bucks, some wire, a bit of solder, it just takes a bit of time. But also not great. It's very unreliable, does work, but not the recommended approach. Off-the-shelf boards are something like $175, at least here in New Zealand, because they usually have to be imported. But, they're way better. Most cases for controllers are designed to fit these boards. You don't have occasionally cold solder joints breaking off or something like that. Why can't we just do that ourselves? Why can't we just figure out how the authentication system works and design our own custom board that is sort of just as good as a Brook board, and that you can just connect everything and it's really nice and mounts in nicely, but it doesn't cost almost $200? Well, let's get into how the PS4 actually handles this kind of license checking. So it's just a standard challenge response authentication scheme. PS4 sends a challenge value, so usually just a randomized value. It'll sign, the device will sign that controller with a private key and then send it back to the console. And it'll also with some identity information so they can do revocation if you've done something they don't like. PS4 sends the challenge to it, challenge, and there's also the identity block, which is a unique serial number and I believe parts of its public key as well. And then if you fail that check, it'll immediately start the 8-minute timer. It'll keep retrying over and over, and if it continues to fail and you pass 8 minutes, it just disconnects the controller. Doesn't even give you a nice pop-up either. It just unplugs it and doesn't tell you. It's not great. There are sort of two modes of doing this. It's in software and in hardware. So either having a microcontroller, like actually the same one that does your input processing, also signing the challenge, or an entirely separate hardware module that does this. And everything is just done over USB HID feature reports. So we'll get into a few of those. This is the reset feature report. So get feature F3. This is the response from the device, and it'll just give the PS4, here's the size of the pages that I want you to send all this information in. So usually it's 56 bytes at a time. It'll get it to send each part of the challenge, and then it'll send the response over in those segments. We wait a little while for it to clear everything and reset the state, and then we can actually send it the challenge. So F0, we have a sequence byte that just counts up, check where in the sequence we are. Page 0 to 4 for when it's 56 bytes, and some data, which is just the actual challenge value. And it will send a few of those, 5 I believe, for the full amount. After that's been done, you also wait a little while, because everything seems to be a little bit timing sensitive with these. So F2 sequence, and it's just a status value 0 or 1. So 0 is ready, 1 is not ready. Once you get a 0 back from that, you can just start querying it for the response. So F1, and it'll just start spitting pages at you pretty much. So from 0 to 18, 56 bytes each time. I think it's 1,040 bytes, something like that. This is what the response actually looks like. It's a signature of the challenge, so it's a SHA-256 of the challenge, and then signs that. And then there's the actual identity block, which is used for sort of vaguely, uniquely identifying the controller. There's a serial, which, if I'm correct, I'm not sure anybody's really looked into it. As far as I know, it's model unique, not device unique. And then the modulus and exponent of the RSA public key, and then it hashes that and signs that as well. So it gets sent plain text and also a signed hash as well. So how does software authentication work? The DualShock 4 does this, the standard off-the-shelf controller for the PS4. And it stores the secrets on flash, which is a choice. It's not bad, not good, you know. But in this case, the early boards expose a debug mode, which, once enabled, just lets you write anything you want to SRAM and just execute it on this controller's microcontroller. And you can see that unpopulated switch there. Once one of those is pulled up, it goes into a debug mode. And Fail Overflow, one of the really big console hacking groups, showed that it's sort of relatively easy to just pull out all of the flash. They do have the key areas protected, but there's some funky stuff with the ARM flash patch breakpoint where you can get around read protections. So that's secrets acquired, I guess. So you've got the keys, but the problem is if you're, say, an end user who wants to build their own controller, that's a relatively simple thing for a person to do, but dumping keys from a very early revision of a board that was never made again and was then patched is not an easiest ask. As well as if you're a really small like boutique vendor, you can't just go dumping keys, flashing them to your devices and shipping them out. You will have a very unfriendly letter from Sony. But what about hardware authentication, the other option? This is an NXP A7105 secure element chip. So every single licensee has one of these on their device's board, and these are given out by Sony to those licensees once you pay their nice little fee. It's a semi-custom chip. It's not in NXP's catalog, and it's essentially a smart card on a chip. Similar idea. And it's just a nice little HV-Son 8 package. Very nice to solder to. Haven't had any issues with it. But hang on a minute. I've seen that before. So that's the brick board from earlier, the off-the-shelf board. They're using the exact same NXP chip, exact same model code as well. They don't have a license from Sony, and that's how they get around the authentication these days. I don't know where they get these from, but apparently this is sort of the accepted way of doing this on the third-party market, is acquiring these chips from somewhere. I would assume the sort of knows a guy who knows a guy type connection ends up getting them these. So let's look into that a little bit deeper. So it's derived from the A71CH, which is the actual public model. It is pretty much identical. And it just executes a Java card applet. So Sony flashes an applet to these chips when they provision them, as well as all the secrets, and it just runs that, and you can send it commands. And it just communicates over I2C. Very simple. Pin 1 and 8 are the two pins for that. And it's smart card I2C on top, which is essentially just spitting APTUs over I2C. Fairly simple. Although NXP does have a doc for it, and it is about 500 pages long. Not sure why. But since it's just I2C, you can just stick a logic analyzer on it. Being a pretty broke student, I can't afford an actually nice logic analyzer, but I do have a pile of Raspberry Pi Picos sitting on my desk. And it turns out there's a few really nice projects that just let you use a Pico as a logic analyzer. I think it's SIGROC, Pico, and MicroLA are the two good ones. So fully open source, using SIGROC to capture the entire authentication cycle start to finish in one capture. So everything is in there. So let's go through those. Same thing really, reset authentication. We have a 80 CLA, so instruction class, that just means it's proprietary. Instruction 48, and then no parameters. So it'll just reset the authentication state, get everything back to normal. And after waiting quite a long time, because this chip is really timing sensitive, you can actually set the challenge. So instruction 44, give it a page size and a page, and then send the actual data of page size bytes, and you just repeat that for every single one you need to do before you hit the end. Then you wait quite a long time after that, and you check the status after every single one of these. I've seen that it takes about 765 milliseconds before you can actually get the response out of it. And you have to query for the status of the chip over and over and over again, or else it'll sort of spit an error code at you that has every single bit set, and the documentation just says other error, which is really helpful. But hang on a minute, I've noticed something weird again. This is a Brook UP5, which is a update to one of their older kits, one of the older boards, so you can just plug this thing in. And this adds PlayStation 5 support to that board. They are using the exact same chip as is found on any other licensed PS4 controller. And they've sort of tried to sand off the chip marking this time, or maybe blur it out. It hasn't really worked, because there's a little bit of an NXP logo visible there. But there's these ones as well, and you can just buy these, and then you don't even have to shuck one off a controller. You just have one of these official chips straight on a nice little board you can plug into something. So now that we have that, we know that you can extract secrets from an early DualShock 4, or you can just yoink a official authentication IC off an actual controller and reuse it, since all the commands are known. What can we do now? Well, this is the inside of that printer from earlier. We can use a Raspberry Pi Pico, a really nice microcontroller, and the open source controller firmware GP2040CE, which is really nice. And that implements key authentication for PS4s and also pass-through as well. So you can just plug in another licensed controller, it'll act as a USB host, and just dump all of the HID requests for authentication over to that one. Don't even have to worry about it. Also some really, really nice open source designs that have come out recently for full controllers. And this one is designed by the same devs as develops the firmware as well. And this has pass-through on board and everything else, all the bells and whistles you'd expect from a fancy controller like this. And also fully open source breakout boards. Same thing as a brick board pretty much, but it costs probably about $20 of materials instead of $175 off the shelf. So it's a little bit nicer and fully open source as well. You can also just, as said, reuse those authentication ICs. I mean, if not pulling one off a controller, you can just buy a Brook UP5 and use that in your own device. Interesting that they've tried to epoxy over it here, I assume trying to hide the fact that they're just using an official Sony part. I'm not sure how well it's worked. So I just want to say a few little quick thanks to a few people. I want to thank OpenStick community, the developers of GP2040CE. Really, really good firmware and a really good technical reference for this whole thing. The Passing Link developers, which is another firmware for STM32s, I believe. Also really good technical reference on how this whole thing works in depth. The RTVS Fight Zone, which is an online fighting game community, a lot of people there who build their own devices and are always helping people out with that as well. And also the Christchurch fighting game community, just shouts out, good people. And that's all from me. Thank you very much.
Busted!